Hi guys, Miss Venable here, bringing you a presentation on covalent bonding. We have already talked about ionic bonding, which is the bonding that occurs between metal atoms and non-metal atoms, and it's an electrostatic bond. And that forms a compound that we call a salt. But now we're going to talk about what happens if we bond non-metals together. So on the right side of your periodic table, there is a stair-step line. Boom, 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 right here. And the nonmetals are the elements that are to the left. Excuse me, I'm backwards. To the right of that stair-step line. The noble gases here in group 18 are not going to form any bonds at all because they already have their stable octet. They are completely reactionless. We call them inert gases. But all of these other nonmetals here, fluorine, chlorine, bromine, iodine, as well as the hydrogen, that nonmetal is kind of hanging out over here, hydrogen. Okay, those are going to form covalent bonds with each other, and some of them can even bond with themselves. We've studied the diatomic elements, or Hoberfinkel, or H7 elements, and they will actually bond with themselves covalently. And what do we call that? Well, when nonmetals bond covalently with themselves, we call it a molecule. So just like ionic bonded metals and nonmetals make salts, covalent bonded nonmetals make molecules. And so if you're trying to figure out, is a compound a salt or is a compound a molecule, look for the metal, because if you see a metal, it's got to be a salt. If you see all nonmetals, it's got to be a molecule. Another way we can tell is by figuring out how strong the electrons are pulled by the atoms that are bonding. So in an ionic bond, the metal really isn't very strong. It does not hold on to its valence electrons, but the nonmetal really pulls valence electrons strongly. And so what happens is the nonmetal will actually yank electrons away from the metal. And I can see here on this chart of electronegativities that on the left-hand side, the metals tend to have really low electronegativities and the nonmetals tend to have really high electronegativities. And if you subtract the values, then you can figure out the electronegativity difference. Okay, whereas if you look at the nonmetals, they're all in a range of, 2.0, 3.5, they're all a little bit higher. So they're very more similar in strength, which means they're going to have to share their valence electrons usually, because neither one of the nonmetals in the bond is really strong enough to pull electrons away from the nonmetal it's bonding with. So here's kind of the rule. If you have two atoms that are bonding, you can look on this chart, look at their electronegativities, and subtract them. Okay, and if the electronegativity difference that you calculate is really low, like 0 to 0.3, then probably they're going to share electrons pretty equally. And so the electron cloud that's created will be very nice and symmetrical, and those are called nonpolar covalent compounds. If the electronegativity difference is a little bit higher, 0.3 up to 1.7, then it's still a covalent bond, but maybe one of the nonmetals is going to pull the electrons a little more strongly, and your electron cloud gets shifted a little bit towards that atom. And so, but it's still covalent because they're all nonmetals. Now, if it's ionic, that means they're really different. So when you subtract, you're going to get a really high electronegativity, like 1.7 all the way up to 4.0. So you can use the numbers on this chart and subtract the things that are bonding to figure out what type of compound you're forming. And there's a couple of videos to watch with an example. If you're clicking through the Google Slides, which I suggest that you do, these green little thing, or the blue links here are highlighted, and I suggest you watch those. Okay, there is a video here on choosing if something is a molecule or a salt. So if you click through the Google Slides, each of these will be explained, but let me give a quick explanation. Look at H2O here. Hydrogen is a nonmetal, oxygen is a nonmetal. So that's a molecule. If I look at CaCO3, Ca is calcium, that is a metal. So you don't need to think anymore, it's got to be a salt. So I put an S there. All right, number 3 is CO2, carbon and oxygen, both nonmetals. So that's a molecule. FeO2, Fe is a metal. So that's got to be a salt. Again, look for the metals and you know that things will be ionically bonded and they form salts. Okay, let's talk about these covalently bonded compounds that we form. We know that they're made of nonmetals. We know that they share their valence electrons, but you may not know that they can actually share different numbers of valence electrons. So sometimes the atoms that are forming the bond will share 2 electrons, and that's called a single bond. Sometimes they'll share 4 electrons. That's called a double bond. And sometimes they'll share 6 electrons, and that's called a triple bond. And the more bonds they have, the more strong the bond becomes. Number 3, the goal of these atoms bonding is to complete their octet. The shared electrons get to count for both of the atoms' octets. And this means that the outer energy level will be completely full for both of them. And when they achieve that kind of configuration, it's called a stable octet. And that's kind of the goal of these atoms when they bond with other atoms, is to achieve their stable octet. And most of the time, that means 8 valence electrons. But the shared electrons get to count for both atoms that are bonding. Number 4, nonmetals can bond in differing ratios. And unlike metals and nonmetals that bond and we do the crisscross, nonmetals bonding can do it in a lot of different ways because they're sharing these electrons, and there's a lot of ways that they can do that. So if I take carbon and oxygen, they can bond in a 1-to-1 ratio, CO, and make carbon monoxide, or they could bond in a 1-to-2 ratio, CO2, and make carbon dioxide. So you can take 2 nonmetals and bond them in, or 2 types of nonmetals and bond them in a lot of different ratios. And so when we write the chemical formulas for covalent compounds, we really have to specify that ratio. And so we do that with subscripts. So carbon monoxide would just be CO, 1 each. But carbon dioxide would be CO, and then we would put a little 2 subscript after the O to say that there are 2 oxygens. Number 6 says many of compounds have common names, and that's really true. There's a few that I really want you guys to know. The first one I really want you to know, and you already know it, is H2O. Nobody says dihydrogen monoxide when they're naming it. Okay, everybody says water. Water is the common name. Everybody uses it. Another common one that I want you guys to know is ammonia. Ammonia is a real common cleaning component in window cleaner and glass cleaner. And the chemical compound ammonia is NH3. It's a nitrogen and 3 hydrogens. I want you guys to know that one. Another one is one we use in our classroom in our Bunsen burners, which is methane. The chemical compound for methane is CH4. CH4 is methane. So there's lots of really common ones that come up, and it's great to know the names for those. Okay, also I want you to know that molecules can be huge. There's a whole branch of chemistry just devoted to studying these huge, huge molecules. Most of them will contain carbon. It's called organic chemistry. You have actually studied some of those huge, huge molecules when you took biology, because DNA, you study DNA, you study lipids. Those are some of the organic molecules, and they call them macromolecules because they're so big. Also, molecules can be solids. They call them network solids like diamonds, and they can be liquids sometimes, and they can be gases. So there's a wide range of physical states that covalent compounds can exist in. There is a video here on some of the properties, but I've listed for you guys the 6 really important ones. Number 1, oftentimes they'll be liquids or gases like H2O, water, or CO2, carbon dioxide. They're going to have a much lower melting point and boiling point than your ionic compounds. Ionic compounds are salts, and they're going to have a really high melting point and boiling point. Like, just imagine you spilled salt on your stove. It's not going to melt. It's just going to sit there. But covalent compounds, it doesn't take nearly as much heat to melt them if they're solid, and if they're liquid, it doesn't take as much heat to boil them. Covalent compounds don't conduct electricity. Unlike ionic compounds have that metal in them, and that acts as a conductor if it's dissolved. But covalents will not conduct electricity. So everybody thinks, oh, water, get out of the water when the lightning starts. Really, it's not the water that conducts the electricity to you. It's really all of the other stuff that's in the water. Covalent compounds are sometimes flammable. There's a group called alcohols. Any type of alcohol is typically going to be flammable, and those are covalent compounds. So not every covalent compound is flammable, but it is possible. Some covalent compounds will dissolve in water, but they tend to be less soluble in water because there's really no ions to pull apart. There's no ions involved with covalent bonding, so they don't really dissolve like the salts do. Okay, here's a list of some common molecules. I've already mentioned the water, I've already mentioned the ammonia, and I've already mentioned the methane, but there's a whole ton here. And some of these are ones that you already know. For example, glucose. You've had biology. I know you've studied glucose because you studied cellular respiration and photosynthesis. So glucose is C6H12O6. And that's a very similar molecule to sucrose, or what we call sugar, which is C12H22O11. Of course, you know O2, that's the oxygen we breathe, and CO2, that's what we exhale. You may not know vinegar, but that's a really common molecule. It's called vinegar, but it's really acetic acid, CH3COOH. Ozone, very important gas that's in our atmosphere, protects us from harmful radiation from the sun. So that's O3. And the main component of our atmosphere, like 78% of our atmosphere, is actually nitrogen, which is diatomically bonded nitrogen, N2. So there's lots of common covalent compounds, and it's useful to know their names. Now, use the common name if you know the common name. If you don't know the common name for a covalent compound, then you have to name it. And because they can bond in lots of different ratios, when you give the name of the compound, you have to specify how many atoms of each type. For example, we're not going to say carbon oxide. We're going to say carbon dioxide because there's two oxygens in it. So here are the rules for naming the chemical names for covalent compounds. There are prefixes associated with how many atoms. So for your prefixes are mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. And you're going to attach that prefix into the front of the name. Also, covalent compounds always end in "ide." So we say carbon dioxide, and we add that di in front of the oxygen so that we know there's two oxygens. And you're going to use the root of these nonmetals. So let me go over the roots of these with you guys. Looking on the periodic table, carbon would just be carb, oxygen would be ox, nitrogen would be nitra, N-I-T-R, oxygen, fluorine would be fluor, F-L-U-O-R, chlorine is chlor, C-H-L-O-R. Sulfur gets a little bit tricky. It's usually best to say sulfide and drop the UR, but sometimes we will say the whole sulfur, like sulfurous or sulfurous. Sulfur gets a little bit confusing, but sulfide is the correct term. Phosphide, phosphor is the root. Bromide would be brome is the root. And hydrogen over here would be hydra, like hydride. And then you just attach the prefix onto the front. So if I had something like CO3, I would call it carbon trioxide. Now, what if you have two of your starting elements like C2H6? C2 would be dicarbon. H6 would be hexahydride. So they're really fun to say. Sometimes you'll get double and triple letters, like carbon monoxide. It would actually be two double O's and make an oo sound. Just drop one of the O's. Sometimes you'll get two I's, like triiodide would be three iodines. Just drop one of the I's. And also, we never start with mono. If your first element has only one, you just say the name of the element. Like we don't say monocarbon dioxide, we just say carbon dioxide. So here's the rules for naming those. And please watch that video. Now, when we want to draw molecules, because we don't want to just talk about them and write their chemical formulas, we want to be able to show what they look like. So the great way to draw molecules is to do something called a Lewis dot diagram that kind of helps us understand how each of the nonmetals is able to complete its octet. And it also allows us to predict if our bond is a single, double, or triple. This determines the shape of the molecule, and the shape of the molecule determines a lot of the characteristics of the substance. So for starters, I just want to introduce you to electron dot models. An electron dot model is just a representation of the valence electrons. Okay, we know how to find valence electrons. It's the Roman numeral at the top of the column. So you are going to write the chemical symbol for the element. You're going to look at the Roman numeral, and you're going to put that many dots around it. There is some little rules about where you put the dots. You can put your first 2 dots either at the top, at the bottom, on the left, or on the right of the symbol. And then after that, you have to put 1 dot on each side and go around either clockwise or counterclockwise. And then you go back and put your next dots paired up. And there is a video there that you guys will need to watch to demonstrate how to do that. So here are a few examples of dot models. I can just take a look at fluorine here. Fluorine here is Roman numeral 7. Okay, so if I was going to do the dot model for this fluorine, I put the first 2 dots together. I usually do it on the right-hand side. The 3rd dot would go on the top. The 4th dot would go on the left. The 5th dot would go on the bottom. Then I would go back around and pair up as much as possible the other 3. The 6th dot would go back to the top, and the 7th dot would go on the left. And you notice there's a dot missing in the bottom because it only has 7 valence electrons. So you can repeat that process for all of the nonmetals there. We really only do dot models for nonmetals. And then what you can do is figure out structure. So how would these atoms fit together? How would they share their valence electrons in order to achieve their stable octet? So there are some rules for drawing a Lewis structure. Rule number 1, you want to choose the central atom. That's either going to be the first atom in the chemical formula or whichever one you have the least of, and it can never be hydrogen. Number 2, you're going to single bond all of your atoms together. And to draw a single bond, you just make a dash. You can do it on the top, the right, the left, or the bottom. And that dash represents 2 electrons. It's a pair of electrons that's being shared. And once you have everything single bonded, you just add in the rest of the dots to complete the octet for all of your atoms. Now to see if you've done it right, and if everything is just single bonded, then you go to your periodic table and you add up all of the numbers of valence electrons for all of the atoms that you have in your formula. And then you count how many you've drawn in your diagram and you see if they match. If you've gotten the correct number of dots and dashes in your diagram, you're done. But if you don't, then you get to change some of your dashes to double dashes. And every time you add another dash, you get to erase 2 electrons off of each of the atoms that you're bonding. And you keep adding double and single, triple bonds, double or triple bonds until you've achieved the correct number of valence electrons. Okay, we are going to demonstrate that in the next slide. It says click to see a video of how to draw a Lewis structure. So I've done formaldehyde, which is H2CO3. And you guys need to watch that video because that will tell you or show you a tutorial on how to apply the rules that I've just taught you. Alrighty, thanks so much for joining me. And this has been Covalent Molecules. Have a great day.